Thank you for joining me to discuss the ins and outs of each of the science and engineering practices. My name is Eddie Walsh, and I want to start us off by having us consider a phenomenon you could explore if you were discussing the properties of volcanoes with your students.
Hi everybody, I'm Mike Poland, the scientist in charge of the Yellowstone Volcano Observatory, and this is the monthly update for December 1st of 2022. I have to admit, it feels a little odd talking about Yellowstone when just a few days ago, Mauna Loa volcano in Hawaii, the tallest active volcano on the planet, started erupting for the first time in 38 years. But I think this provides a neat opportunity to talk about the parallels and differences between Hawaiian volcanism and Yellowstone volcanism. There's actually some interesting similarities. Most volcanoes on Earth are located at the boundaries of tectonic plates, the plates that move around and make up the surface of the Earth, where they come together, where they spread apart. That's a very common place to see volcanoes. But both Yellowstone and Hawaii occur in the middle of tectonic plates, far from the boundaries. That's because these sorts of volcanoes are powered by what we call hotspots. These are anomalous areas of melting that are sourced deep within the Earth. And as they rise up, they sort of burn their way through the tectonic plate, create a volcano. But as the tectonic plate moves, it gradually carries the volcanoes away from the hotspot source, and the hotspot has to punch through again. So for hotspots, you actually see a trail of volcanoes that gets older and older and older the farther away you get from the hotspot. In Hawaii, this is a trail of old islands and seamounts that stretches all the way back to Russia and Kamchatka. And in Yellowstone, we can see that trail stretching across southern Idaho, the Snake River Plain, with the volcanoes getting older and older the farther away you get. Now, there are some important differences between the volcanism in Hawaii and Yellowstone. Now, Hawaii is on an oceanic plate, and that allows magma to rise more quickly. It doesn't stick around and change its composition in the crust. It has a basaltic composition that's got less silica in it, it's more fluid, and you get these runny lava flows that Hawaii is famous for. It builds these shield-like volcanic shapes. But Yellowstone is on a continental plate, and so the magma rises much more slowly, eruptions are much less frequent, and the magma that's generated has a different composition, higher in silica content. It's called rhyolite, and it has much more potential to be explosive. So because of the different settings, oceanic and continental, you get fluid and frequent eruptions in places like Hawaii, and less frequent eruptions in a place like Yellowstone, this sticky lava that can occasionally explode with extreme violence. So some interesting parallels between these hotspots in Hawaii and Yellowstone, but also some very important differences because of their setting. Okay, now let's talk about what we observed in Yellowstone over the last month in terms of seismic activity, deformation, and geysers.
November was a pretty average month for seismicity in the Yellowstone region. The University of Utah seismograph stations, which is responsible for the operation and maintenance of the Yellowstone seismic network, located 174 earthquakes during the month. The largest was a magnitude 2.6, located about halfway between Mammoth Hot Springs and Norris Geyser Basin. This is part of a sequence that has been ongoing since late July of this year. And during this month, 123 of the earthquakes located in Yellowstone were part of this sequence. So pretty average for Yellowstone, with this continuing sequence of seismicity occurring between Norris and Mammoth. Turning now to ground deformation, we've seen not a whole lot of change over the last few months. This is the last 2 years of vertical deformation on the east side of the caldera at the White Lake GPS station. Each one of these blue dots represents 1 day of data, with downward trends indicating subsidence and upward trends indicating uplift. And the overall trend since 2015 has been subsidence, and it's interrupted during the summer months as groundwater recharge from snowmelt sort of puffs up the ground like a sponge that's soaking up water. And then outside of the summer months, you see that continued subsidence. So here's the summer disturbance in 2022, and then we have some sort of chaotic changes towards the end of this sequence in November, and this is because of a large snowstorm that struck in November. This covers the GPS antennas and distorts the signals, and so this is something of an artifact. So there hasn't been a whole lot of net deformation, total deformation, over the last few months at Yellowstone. The same is true if we look over at the west side of the caldera at a station that's located near Old Faithful. Overall subsidence over this 2-year period, and you can see this disturbance that occurred in November due to the heavy snow. We also see this at Norris Geyser Basin. Not a whole lot of changes over the last couple of years, and then there's quite a dramatic artifact right here due to that snow accumulation on the antenna. Even if we go outside Yellowstone National Park, and this is a GPS station that's in Paradise Valley, Montana, so north of the park, you can see that same sequence of disturbance due to the heavy snow that fell throughout the region. So in November, there was a few centimeter artifact that was caused by that heavy snowfall. It doesn't affect our overall impact to monitor the region because We would expect to see much larger changes than these small deviations if there was something going on. But it's an interesting example of just how sensitive these GPS stations are to even changes in weather and how they can pick up all kinds of interesting signals. And then finally, moving to geyser activity, and everybody's favorite geyser, Steamboat Geyser, the tallest active geyser in the world. It did have an eruption in November, on November 5th, right here. This is the temperature record in the Steamboat outflow channel, basically the water temperature. You can see that spike, that's the eruption, and then the temperature drops back down and goes basically down to zero, freezing temperatures in the cold months there. And then we started on the 20th of November seeing an increase in minor eruptive activity. So there's clearly water coming out of the geyser right here, and that suggests that Steamboat is not done erupting. Hopefully we'll see another eruption in December. So far in 2022, there have been 10 eruptions of Steamboat Geyser, quite a few less than we've seen in previous years, but still more than is usual for Steamboat. So it's still putting on quite the show.
Well, that does it for the Yellowstone Volcano Observatory's monthly update for December 1st of 2022. Now remember, if you'd like more information, you can always feel free to email us at yvowebteam, all one word, at usgs.gov. And if you'd like more information on Yellowstone or the activity that's occurring at Mauna Loa, you can find us on social media, USGS Volcanoes. We have a very large web presence and putting lots of information about the eruption online. And you can also subscribe to get volcano alerts in your email through the Volcano Notification Service. So check that out if you'd like more information. Thanks everybody, stay safe, stay healthy. We'll see you next month. Bye-bye.
A quick and easy way to get students thinking about what they just saw would be to have them document what they notice and what they wonder about the video they just watched. After some quiet time to work independently, students can share out their notices and wonders in their pairings or groups before collaborating and selecting their top notices and wonders. As we lean into the science and engineering practice of constructing explanations and designing solutions, this would be a good opportunity to ask students to consider what they noticed and wondered about the phenomenon that might inform how scientists have come to explain volcanic activity taking place in the middle of a tectonic plate, like in Yellowstone or Hawaii. You could even have students examine maps or other data to produce more notice and wonders for their inquiry. If a student or group of students already began examining or questioning the explanations offered by scientists for this volcanic phenomenon, be sure you use that student-generated observation to lead into this next part. After having students consider the phenomenon generally, you can then have students reflect and consider what they notice and wonder about the video they just watched, paying special attention to the explanation offered through the video by scientists. Not all students are equipped with a sense for constructing scientific explanations. While it's easy to offer students explanations, by explaining everything for our students, we deprive them of authentic scientific learning. It is important to set aside times for students to build their own explanations, so much so we adopted it into our Idaho Science Standards. I want to go ahead and fully introduce myself. My name is Eddie Walsh, and I am the Region 6 Instructional Science Coach working with the Idaho Department of Education. I'm based out of Idaho Falls, but myself and the other Idaho Science Coaches are happy to meet you wherever you are in your science education journey. Our sole focus is to help teachers plan, teach, and assess around the Idaho Content Standards for Science. I want to take this opportunity to focus on how we can approach the science and engineering practice of constructing explanations and designing solutions. If you have further questions about how the Idaho Science Coaches can help you with your teaching goals, feel free to reach out to me at my email or visit our Idaho Science Coach website via the QR code or Idaho Department of Education website. When the National Academies of Science, Engineering, and Medicine developed the 3 dimensions of the framework for K-12 science education in 2011, the science and engineering practices were recognized as perhaps the largest shift educators would need to address to engage students in the immersive experience that is science. Asking students to construct explanations and design solutions means helping students figure out the same theories that underlie disciplinary core knowledge in science without front-loading all of our information through lectures and readings. Students need to familiarize themselves with the methods for creating sound scientific explanations and experience the failure of non-functional design solutions. I would make it my recommendation right now. If you can, lead with an opportunity for students to construct explanations independently, and do it as often as you can. While students may initially find coming up with explanations and solutions to be difficult and time consuming, with frequency and practice, students will be able to find resolution in more challenging situations. Explanations and solutions from the past offer students constructive insights into how scientists and engineers in the past confronted scientific and practical problems. After riding a trolley car in a snowstorm and seeing the trouble trolley drivers had to go through to remove snow from the front windows, Mary Anderson thought up the windshield wiper to keep windows clear. The design was seen as so important it was adopted by vehicle manufacturers almost universally. Joe Farman was able to determine that there was a hole forming in the ozone layer over Antarctica. His proposal of curbing chlorofluorocarbon emissions halted the spread of the hole and proved an ability to work toward restoring the ozone layer through mitigation efforts. And theories like the Big Bang Theory do not pop up overnight. George Lemaitre took the theories of many scientists to develop an understanding of the expanding nature of the universe, which was translated into the Big Bang Theory and underlies many predominant theories concerning the origins of the universe. The creation of each of these explanations and solutions required scientists to manage a large conceptual shift in understanding, which they then clearly and concisely fold into a theory or solution. Integrating the science and engineering practice of constructing explanations and designing solutions needs to look differently at each step in the K-12 student experience. We, as teachers and administrators, recognize when one grade band or another doesn't provide students opportunities to advance in their explaining and designing skills, we limit student potential throughout their entire learning progression. If students are not provided the opportunity to theorize or solve problems in their education, they are not gaining the skills that are required of them to be productive in science or other facets of their lives. The K-12 Skills Progression document on the Idaho Department of Education website breaks down the experiences students should be able to navigate to stay on track with peers locally and nationally. This document provides teachers with starting points for imagining a range of student experiences that allows students to build competency in the range of skills associated with developing explanations and solutions. When laid out in this way, we can provide clearer feedback to students and scaffold more for students who find generating explanations difficult, or challenge students who have shown early mastery in the SEP. It becomes important to remember students often do not master a standard in a single instance, so planning several opportunities for students to flex all of their explaining and problem-solving skills within a grade band is critical for all students to stay on track in their science progression. If you are considering introducing scientific work centered around developing explanations or solutions, you may consider referencing the work of Dr. Shannon Cobbs-Nowotniak at Idaho State University. As a geoscientist, Dr. Cobbs-Nowotniak has led several investigations into how volcanic surfaces, like those found in craters of the moon in southern Idaho and the islands of Hawaii, can serve as learning environments for scientists hoping to gather samples and data from other planets. Her work is helping astronauts train and troubleshoot problems they might experience in space before those issues arise, so we can gather more valuable data from future space missions. If you are looking for strategies to bring explanation construction to the forefront of your teaching, I have a few materials you may consider if you feel this will be a rough start. Sentence stems help all students access the practice of constructing explanations so students don't find themselves with nothing to write about. Similarly, science talk strategies offer students guidelines for what discourse in science should sound like. A CER statement lays out the claim, evidence, and reasoning of an explanation, offering structure and logical scaffolding to help students construct sound explanations. Design thinking is a broader instructional strategy that asks students to speak with people in their communities to get a better sense of underlying problems that they can address, and then asks students to produce and explain their own solutions. Science notebooks give students a place to store their ideas and practice coming up with explanations and solutions tied to the disciplinary knowledge embedded in a lesson or unit. If making time for science and engineering practices seems difficult, consider going deeper into units centered around constructing explanations and solutions and pulling back on content-heavy instructional days with lectures and worksheets. Thank you for your time as we covered how constructing explanations and designing solutions can help students access authentic science learning opportunities. Hopefully the understandings and strategies outlined in this video make it less stressful to bring instruction around science explanations to your students. please do not hesitate to reach out to me or anyone on the Idaho Science Coach team to clarify anything about the standards.